Let's take a look at section 5.5. In this section, we're going to look at rational and irrational numbers.
The main thing about this section is looking at rational numbers versus irrational numbers. And so let's start with a definition of a rational number, and that is that it can be written as a fraction or a ratio. So let's look at several examples. We can look at any whole number. 3 can be written as that number over 1, so that can be written as a fraction. So all of the natural numbers, whole numbers that you know, those are all rational numbers. A regular fraction, 2/5, that is also a rational number. You also have rational numbers that you might see as decimals. So if you have a repeating decimal, for example, 1/3 is 0.333333 forever, and you can oftentimes see that written as with this bar, and so 0.3 with a bar over it, that means it's a repeating decimal, and that is actually also a rational number. You might see other repeating decimals that look a little different, but for example, this one here that is 0.21, that repeats over and over again. And then any terminating decimal, so like for example, 1/2 can be written as 0.5. So those are all rational numbers. Now let's take a look at the irrational numbers. They cannot be written as a fraction or a ratio. And so examples of these, the first one is pi. Pi is a number that sometimes you may hear that we call it 3.14. That's an estimation, but this is actually a number that goes on and on and on forever. And so if you notice here the dot, dot, dot at the end, that means it goes on and on and on forever. So there are infinitely many numbers that make up pi. And so that is an irrational number. There's also another number called e, which is 2.71. We call it 2.72 as an estimation, but you can see it has a similar feature as pi. And also, I want you to be aware of fake repeating decimals. That's my terminology, this fake. But if you notice here, you have 7,112, 1,112, 1,1,112. So even though this is definitely a pattern, this is not a repeating decimal. It's a pattern, but it's not a repeating decimal. And so this would actually be considered an irrational number. And then lastly, if you have the square root of a prime number, the square root of a prime number is going to be an infinitely long number as well. And so that is going to make that an irrational number. All right, so now let's look at a few other examples. Okay, in these examples, you're going to be asked to simplify these radicals. We call these radicals because they have square roots, and the square roots are often referred to as a radical. And so what we're going to do here is look at our first one, 5 times the square root of 12, and we're just going to concentrate on that square root of 12. Now, I want you to think of a way to factor the square root of 12 into two factors that multiply together to give you 12. But I need one of those factors to be a perfect square. So when I say perfect square, I mean 2 times 2 is 4. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on, which makes these numbers 4, 9, 16, 25, and so on perfect squares. So I need one of the factors of 12 to be a perfect square. So I'm going to actually break that square root of 12 into the square root of 4 times the square root of 3, because 4 is the perfect square. Now you can take the square root of 4 and get 2, and then all you have to do is multiply 5 times 2, and you get 10 times the square root of 3. Now you want to always look, and if you can simplify that radical any more, then you need to do so. But in this case, the square root of 3 is a prime number. 3 is a prime number. So that is as simple as it gets. So that would be our final answer in simplified form. Now let's look at 2 times the square root of 250. All right, we're going to do the same thing. We're going to break 250 up into the square root of perfect square times the other factor. And so that's going to be the square root of 25 times the square root of 10. Now, then you can take the square root of 25, which is 5. So you're going to have 2 times 5 times the square root of 10, which is 10 times the square root of 10. Now let's think about factors of 10. So I know that there's only 1, 2, 5, and 10. And none of those are perfect squares. So I cannot simplify the square root of 10 anymore. And so this is actually your final answer. All right, let's simplify a few more expressions. So now you're going to have, you've got an example here, simplify the expression. You've got to go back to the beginning of the semester when we talked about order of operations. You remember we used a little phrase called PEMDAS, which stands for parentheses, exponent, multiplication, division, and then addition, subtraction. Now, I want you to kind of consider that everything underneath this square root sign, that's going to be kind of like a parentheses. I've got to do everything underneath this first. So because it's trapped in this big, huge parentheses. So I'm going to go under here, and now I'm going to start my order of operations again. So these parentheses are just being used to separate these numbers, but there's no math that's being done inside of those parentheses. So I can kind of ignore those for right now. But we do have this exponent, so that's going to be our first step. So 8 squared is going to be 64. Okay, now I go to multiplication division, and this is where you do in order from left to right. And so I'm going to first do this 4 times 6, and then I'm going to multiply that times the 2. And so you have 64 minus 24 times 2. That would be 64 minus 48, which is the square root of 16. So now I've done everything underneath that radical. So now I'm ready to take the square root of 16, which turns out to be 4. And so that would be your final answer. You're also going to have a few problems that I call ladder word problems. They all end up dealing with a triangle in some form. So I wanted to go over this with you just to make sure that you understood how these work. So read the problem first. How far from the base of a building must a 10-foot ladder be placed so that it reaches 6 feet up the wall? Now, the first thing that I do, I read the problem a couple of times, and then I try to draw a picture. So here's your building, and thankfully I'm drawing this picture through PowerPoint and not drawing it on a whiteboard because I can't even draw buildings and ladders really well. So this will actually look a lot better. So here's my building. So you kind of get the point. We've got a ladder leaning up against a building. Okay. Now it says here that this ladder is 10 feet. So, and then we want to know, they said it's going to reach 6 feet up the wall. And the question then is how many feet should the base of that ladder be from the wall if you need it to be 6 feet high? Okay, so what we're going to do here is we're going to kind of draw in, notice I put in here this is the ground level right here, and this is what I'm looking for, this distance. But if you notice, this forms a triangle, and there are features of triangles that will help us solve this problem. This is actually a special triangle because, I don't know if you remember or not, but if you see a box in the corner, this is called a right triangle because this forms a right angle, which means this is 90 degrees, okay? There is a special property about these right triangles, and it is called the Pythagorean theorem. Now, the Pythagorean theorem, you can read about it in your text, but it basically says you take the 3 sides of a triangle, and so you have A, B, and C. And the theorem states that a squared plus b squared equals c squared. So let's label our triangle. First, we're going to label the 6-foot side as A. B is going to be the bottom side. So these are called your 2 legs. A and B is always your 2 legs. It doesn't matter really which one is A and which one is B. But C has to be called your hypotenuse. It's always going to be the longest side And C is also going to always be across from your right angle. So whatever side is across from your right angle has to be your C side, okay? So now I'm going to plug in these values into this equation that I have here. And so notice here that because A was equal to 6 feet, then I put in 6 over here. So 6 squared plus B is my unknown, so that's B squared, and it equals to C squared, which is 10. So this is 10 squared because that's the length of the ladder. Now I'm going to work out a few of these exponents. So I get 36 plus B squared equals 100. Now you have to go back to algebra to learn how to solve this. So basically we're going to solve for B. But we've got to get this B by itself. So I need to get rid of 36. And so by doing that, I subtract 36 from both sides. Remember in algebra, whatever you do to one side, you have to do to the other side. So 100 minus 36 gives me 64. This 36 goes away, and I'm left with B squared equals 64. Now, to get rid of this, I don't need B squared, I need just B. And so to get rid of that square, you do the opposite of that, which is actually the square root. So I'm going to take the square root of both sides because, again, whatever you do to one side, you have to do to the other. You're going to turn out to get B is equal to 8. Actually, by definition, proper definition, when you take this B could also be -8 because -8 squared would also give me 64. But we are talking about a distance here, and distance is always measured in positive values. There's no such thing as a negative distance. And so we're only going to be looking for the positive value 8. So it turns out that the answer is 8 feet. The base of the ladder must be placed 8 feet from the wall, from the building, so that it would reach 6 feet high. Okay. Now you're going to have several problems that are going to be similar to this. They are all going to end up being some type of triangle problem, and you are going to use this very same formula to solve them. So hopefully this will get you through the problems in this section. Let me know if you need any other help.